For decades, humanity has looked toward the sky with a sense of awe, curiosity, and fear. Out there beyond the blue curtain of our atmosphere drifts a silent population of rocks, mountains, and metallic fragments left over from the birth of the solar system. They follow ancient paths around the sun, crossing and recrossing the orbit of Earth in a cosmic dance that has lasted billions of years. Most of them never come close to us. Many never even enter our region of space. But a few do. A few wanderers stray uncomfortably near our fragile home world, slipping past with little warning, sometimes discovered only after they have already passed by. These are the near-Earth objects, the ones NASA carefully tracks every hour of every day. And among the thousands cataloged, so far lies a much smaller group that has caused concern. A list known unofficially as the high-risk objects. Those with orbits that bring them just a little too close, with sizes too large to ignore, and with predictions that include a small but real probability of a future impact. This list is not a public Hollywood-style collection of doomsday threats. It is a cold scientific effort that changes constantly as new observations improve trajectories. But the existence of this list represents something profound. It reveals that our planet lives in a cosmic shooting gallery. Even if the probability of impact is low, the consequences could be monumental. And so NASA watches. Telescopes across Earth watch. Space agencies in Europe, Asia, and South America watch, all waiting for the faint glimmer of a new asteroid that might require humanity's full attention. It might surprise many people that the first serious attempt to catalog near-Earth objects began only in the late 20th century. Before that, no global program existed to monitor the countless drifting bodies that share the inner solar system with us. Astronomers knew these objects existed. They knew the planet had been struck many times in the past. But systematic surveys were rare, funding was limited, and computing tools were primitive compared to what is available today. That changed after several so-called close calls that shook the scientific community. One was the discovery of asteroid 99942 Apophis in 2004. Early calculations suggested a non-zero chance that Apophis might strike Earth in 2029. Later observations ruled that out, but the event exposed how blind humanity was to incoming objects. Another turning point came in 2013 when a previously undetected meteor exploded over Chelyabinsk, Russia. It caused widespread damage and injuries, even though it was small by cosmic standards. The shockwave shattered windows and reminded the world that a stone traveling faster than any bullet is not a threat we can afford to ignore. In response, NASA expanded its Space Guard surveys, created the Near-Earth Object Observations Program, and began collaborating with observatories worldwide. The goal was clear. Find 90% of all near-Earth objects larger than 1 kilometer, the so-called planet killers. Then find the rest down to 140 meters, a size that would devastate a regional area. Over time, the catalog grew from a few hundred objects to tens of thousands. Their orbits were tracked, refined, and stored. And from these calculations, a subset naturally emerged. A group of objects with unusual orbital behavior, repeated close approaches, or long-term uncertainties that merited extra monitoring. These would form the backbone of NASA's internal high-risk watch list. Contrary to popular imagination, this list is not a secret vault guarded behind steel doors. It is a database that evolves as astronomers update information. Any object whose orbit crosses within a certain threshold of Earth is automatically assigned a risk rating. This rating is based on 2 factors: the size of the object and the trajectory uncertainty which could intersect Earth's orbit at some future date. Even a tiny asteroid with a poorly known path can show up on the list temporarily until better measurements refine its location. NASA uses systems like Sentry-2, which continuously runs orbital projections extending decades into the future. It tests thousands of possible paths, simulating gravitational interactions with planets and small perturbations that can change an asteroid's flight over time. If any of those future paths intersect Earth, even slightly, the asteroid is flagged for closer study. The objects that remain after repeated confirmation are the ones that concern astronomers the most. They're not guaranteed to hit Earth. A single updated observation from a ground telescope or radar system can sometimes eliminate the risk entirely. But until that new data arrives, they remain in the high-risk category. This is the quiet reality behind NASA's monitoring efforts. The danger is not always dramatic. It is the mathematical uncertainty that keeps scientists awake at night. The knowledge that something large could be approaching, yet still hidden by the glare of the sun or unobservable from Earth for months at a time. Among the objects monitored closely are those roughly 100 to 300 meters across. These are not global extinction objects like the asteroid that ended the age of dinosaurs, but they are powerful enough to destroy a city or flatten a region the size of a small country. The impact energy of such an object would exceed the largest nuclear bombs ever built. One of these asteroids, often referenced by risk analysts, is an object that astronomers track every few years when it becomes visible again. Its orbit brings it moderately close to Earth, but it is also influenced by the gravitational pull of Venus and Mars, which introduce slight variations. Each time it passes near Earth, scientists study it again, refining its orbit and reducing uncertainties. The more times it is observed, the less risky it becomes. But until the orbit is known with absolute precision, it stays on watch lists. NASA also pays attention to objects that could be delayed threats. Some asteroids do not pose a risk in the next decade, but may approach more dangerously in the next 50 or 100 years. These long-term threats are kept on the list, not because of immediate danger, but because of the need for early preparation. If an asteroid discovered today is predicted to approach closely in the year 2120, humanity has time to experiment with deflection technologies. Technologies like kinetic impactors, gravity tractors, or even advanced propulsion systems could gently alter its path over generations. But that possibility exists only if scientists maintain detailed awareness of these objects long after public attention fades. The process of identifying high-risk objects is more complex than pointing a telescope at the sky. Many near-Earth objects are faint, dark, and small. Even large ones can go unnoticed if they approach from the direction of the sun, because telescopes on Earth cannot observe the daytime sky. To solve this problem, NASA and other agencies use infrared telescopes, wide-field cameras, and automated scanning software. Every night, observatories capture thousands of images. These images are searched for faint moving dots. Once detected, the object's movement across several nights is analyzed to determine its orbit. But this early orbital calculation is often imprecise. The asteroid might be visible for only a few days before it moves into a region impossible to observe. In those cases, scientists must wait months or years until the asteroid returns. During that waiting period, its predicted orbit contains uncertainty, and that uncertainty can include possible Earth intersections. This is how many objects temporarily appear on the high-risk list. This also explains why the list can grow unexpectedly whenever surveys discover new objects. A newly found asteroid might be flagged immediately, not because it is truly dangerous, but because the orbit is still poorly known. Over the following months, astronomers around the world coordinate to gather additional observations. Sometimes an asteroid becomes visible in radar systems, which provide extremely precise measurements. Radar can determine its distance, rotation, shape, and velocity with remarkable accuracy. This often eliminates any threat. But until that happens, the asteroid remains under careful monitoring. One of the most fascinating parts of NASA's tracking system is the classification of potentially hazardous asteroids. These are objects at least 140 meters in size that can approach within a narrow distance of Earth. Many of the asteroids on the high-risk list are part of this category. They have orbits that cross Earth's orbit at certain points, and the timing of their approach can vary slightly with each cycle. The variations arise from gravitational nudges by planets, solar radiation effects, known as the Yarkovsky effect, and mutual interactions between asteroids themselves. Over long timescales, these small nudges can accumulate into significant changes. An object predicted to pass safely in 2060 might appear more concerning after recalculations in 2080. This is why constant monitoring is essential. The cosmos is dynamic, and even minor changes can shift the future. Scientists use advanced simulations to model more than 1,000 potential future trajectories for each object. Each simulation includes slight differences in initial conditions, similar to rolling the dice thousands of times with slightly different numbers. Some of these simulations yield safe outcomes. A few may yield impacts. The impact probability is calculated based on how many of these simulated paths intersect Earth. If the number is above a certain threshold, the asteroid is officially labeled high risk. This does not mean disaster is imminent. It simply means that until further observations narrow down the asteroid's true path, the possibility remains. The existence of this evolving list has influenced NASA's broader decision-making. It has inspired new missions, such as the Double Asteroid Redirection Test, which successfully altered the orbit of asteroid Dimorphos in 2022. This mission proved that humanity could nudge a celestial body off course. Although Dimorphos was never a threat, the test demonstrated a strategy that could one day save Earth from a real danger. In addition to this, NASA is developing new space-based observatories designed to spot incoming objects from vantage points that ground telescopes cannot reach. One such mission is designed to operate in infrared wavelengths, allowing it to detect dark asteroids invisible to optical instruments. These dark objects often reflect very little sunlight, making them nearly impossible to detect until they are close. The high-risk list is therefore not a source of panic, but a tool for preparedness. It allows scientists to identify which objects require urgent tracking and which can be safely deprioritized. It also informs policymakers who must decide how much funding is necessary for planetary defense efforts. And it serves as a reminder to the public that vigilance is essential. Humanity cannot control the cosmos, but humanity can observe it, understand it, and over time learn how to protect itself. Many people wonder what would happen if NASA discovered an asteroid truly on course for Earth. According to official protocols, the first step would be verification. Multiple observatories would gather data to confirm the threat. The object's orbit would be recalculated with high precision. If the risk remained significant, NASA would notify global agencies, including the United Nations Office for Outer Space Affairs. A planetary defense conference would be initiated. Countries would pool resources and strategies. Engineers would begin designing possible deflection missions. The timeline for intervention would depend entirely on the object size and how much warning time humanity had. If the warning were 50 years, the intervention could be gentle and methodical. If the warning were 10 years, the response would need to be faster, involving kinetic impactors or even multiple spacecraft. The most feared scenario is the short-notice discovery known as a late detection. This is when an object approaches from the solar glare or from behind the sun, giving Earth little time to react. Fortunately, most large asteroids have already been detected. The majority of late detections involve smaller objects that burn up in the atmosphere or cause limited damage. But NASA's quiet concern remains with mid-sized objects between 50 and 100 meters. They are difficult to detect, yet dangerous enough to cause severe regional destruction. These objects are monitored carefully, and many of them appear temporarily on the high-risk list until their orbits are fully established. Another important factor is the physical composition of these objects. Not all asteroids are solid rocks. Some are rubble piles held together by weak gravity. Others are metallic bodies that would survive atmospheric entry far better. Some rotate rapidly, complicating deflection strategies. Some contain hollows or fractured interiors that could absorb an impactor without significantly changing trajectory. These physical details matter enormously. When an object appears on the high-risk list, NASA works to characterize it using radar imaging and spectroscopy. They attempt to determine its density, rotation speed, composition, and shape. Deflection missions require precise knowledge because the wrong approach could make the situation worse. A kinetic impactor striking a rubble pile might break it apart, but still send debris toward Earth. A gravitational tractor would work better for loosely bound objects, gently tugging them off course over years of sustained influence. Understanding these physical traits is also vital for predicting impact consequences. A metallic asteroid would penetrate deeper into the atmosphere and cause more explosive force at ground level. A stony asteroid might fragment in the air, spreading damage across a wider area. This is why the study of near-Earth objects is not only about preventing impact, but also about understanding what would happen if prevention fails. Impact modeling allows emergency planners to prepare evacuation strategies, estimate damage zones, and develop response plans. Even if the risk is small, the knowledge gained is invaluable. The high-risk list also contains objects that are not well understood because they have been observed only briefly. Some discoveries occur during fast flybys where the asteroid is visible for just a few days. In such cases, astronomers capture every piece of data they can, but the orbit remains uncertain. The asteroid then disappears into the darkness for years. During this time, its predicted path grows fuzzier. The next time it is scheduled to return, it may be extremely faint or difficult to locate. In some cases, objects are temporarily lost. Astronomers must research the predicted region and hope to detect the object again. When it reappears, its orbit can be recalculated, and often the risk drops to zero. But until then, it sits on the list, an unresolved question in the sky. There have been instances where an object thought to pose a threat was later re-identified and moved out of the danger category. These stories highlight the importance of persistence and patience in asteroid monitoring. Sometimes the process can take decades, especially when the object follows a long orbit and returns only once every few decades. The long wait can build suspense among scientists who track it. They know that each observation window is precious. If the window is missed or if weather conditions interfere, the opportunity might not come again for years. This is one reason why global cooperation is vital. Observatories in multiple countries can cover for each other, ensuring that critical data is collected when needed. Though much of the focus is on asteroids, NASA also tracks comets that pass near Earth. Unlike asteroids, comets contain volatile ice that can erupt under solar heating, altering their path unexpectedly. This makes their trajectories even harder to predict. A comet that appears harmless at one observation could develop a jet of gas the next month that pushes it slightly off course. Over time, these tiny pushes accumulate. Comets therefore appear on high-risk lists more frequently when first discovered, until their activity levels become predictable. Fortunately, most comets that come near Earth are large enough and bright enough to be detected early. But a few exceptions exist, especially for long-period comets coming from the distant Oort cloud. These visitors can appear suddenly, shining faintly against the stars, and arriving on trajectories that may not repeat for hundreds of thousands of years. When such a comet is discovered, NASA immediately analyzes its orbit. Even if the threat probability is small, it still becomes a subject of intense focus. While the public often imagines a world-ending collision, NASA's primary concerns are more moderate but far more realistic. An object between 100 and 300 meters in diameter could cause catastrophic losses if it struck a populated region. These objects appear frequently on the high-risk list because they are common in the inner solar system and harder to detect than giant kilometer-sized asteroids. The list therefore prioritizes objects of this size, monitoring any that pass repeatedly close to Earth. Each close pass gives scientists the chance to refine measurements, checking whether its orbit drifts significantly over time. If the drift becomes concerning, the object receives heightened priority. There is a misconception that the list represents some sort of classified threat. In reality, the vast majority of information is publicly accessible through NASA's databases. The term secret list arises mostly from misunderstandings and public speculation. What people imagine as secret is simply the technical analysis that is constantly updated, recalculated, and communicated to scientists worldwide. Although NASA does assess threat probabilities internally, nothing about the process is hidden. What remains invisible to the public is the quiet dedication of scientists who monitor the sky every night, often without recognition, making sure Earth remains safe. The story of NASA's high-risk monitoring program is ultimately a story about responsibility. Humanity now possesses the technology to detect most incoming threats, though not all. It has the ability to calculate future trajectories with extraordinary accuracy. It even has the early foundations of planetary defense capabilities. But this is only the beginning. Space agencies are now planning new missions, such as next-generation infrared observatories that will provide unparalleled visibility of the inner solar system. These missions could detect tens of thousands of objects that are currently unknown. Among those objects, some may require careful monitoring. The high-risk list of the future might look completely different from today's version, but the existence of such a list symbolizes progress. A century ago, humans had no idea what objects drifted near Earth. Impacts came without warning. Now humanity possesses the ability to predict cosmic encounters decades before they occur. This is one of the most remarkable achievements of modern science. It is a sign that humanity is slowly taking its place as a species capable not only of exploring the universe, but also of defending itself from its dangers. Imagining the future provides perspective. Picture a world 50 years from now where advanced telescopes orbit the sun at various vantage points. Each one watches for faint glimmers of motion against the star field. Artificial intelligence analyzes millions of images in real time. Drones mounted with cameras sweep across the dark side of the moon. Spacecraft drift near Earth waiting to serve as planetary defense platforms. In this future, the high-risk list is not a frightening roster of possible impacts, but instead a constantly updated stream of minor orbital corrections, monitored by technology far beyond what exists today. Humanity no longer fears surprise impacts because sensors detect incoming objects long before they become dangerous. But until this future arrives, the list remains essential. It is the watchtower from which astronomers keep guard. It is a reminder that we inhabit a world surrounded by wandering stones. And it is a testament to the resilience of a species determined to survive. Every object on that list represents a challenge and an opportunity. A challenge to understand the universe more deeply and an opportunity to test humanity's capacity for foresight. Ultimately, NASA's high-risk list is not about fear. It is about vigilance, intelligence, and preparation. It represents the quiet work of thousands of scientists who have dedicated their lives to studying tiny points of light. It represents decades of progress in computing, astronomy, and planetary defense. And it represents humanity's commitment to safeguarding its future. Each asteroid monitored, each orbit recalculated, each mission designed brings us closer to a world where cosmic threats can be managed with confidence and certainty. We are no longer blind to the dangers that drift in the darkness. We are learning. We are watching. And with each passing year, we are becoming more capable of protecting the only home we have. In this long and ongoing journey, NASA's evolving list of high-risk near-Earth objects serves as both a warning and a beacon. A warning that space is not empty and that vigilance is essential. And a beacon that guides our scientific efforts, encouraging us to explore, discover, and defend. The story is far from over. New objects will be discovered. Old ones will be reevaluated. Technologies will advance. And humanity will continue its watch from beneath the stars, aware at last that our future depends not on fear, but on knowledge, preparation, and the unending quest to understand the universe that surrounds us.